So last time we talked about the terrestrial biosphere and the different types of terrestrial biomes. We also examined climate diagrams and how to interpret them and what that means for a specific biome in terms of precipitation and temperature. And we also covered vertical zonation or altitudinal zonation. Today, we're going to talk about both marine and freshwater ecosystems on Earth. Here is a satellite image showing the amount of productivity in the world's oceans. This was put together in part by a team at NASA. And what we can do is measure the amount of chlorophyll in a water body. Chlorophyll is a proxy measurement for productivity because chlorophyll is in photosynthetic algae, as we'll talk about in the upcoming slide. So what this shows us is that we have dark blue oceans that are characterized by low chlorophyll measurements, meaning these are biologically impoverished. There's not a lot of photosynthesis happening here. But as we trend over to green and yellow colors and even red, we have lots of more photosynthesis measured through those chlorophyll measurements captured by satellite data. So what you might notice here is that there's large expanses of the open ocean where there's not a lot of productivity happening. Instead, that productivity tends to be concentrated along coastlines, and that has to do with nutrients pouring in from the terrestrial realm. And so just a little bit in general about these marine ecosystems. Most marine communities depend upon photosynthetic organisms to fuel their productivity. Okay, and these photosynthetic organisms are phytoplankton. Phytoplankton are defined as tiny, free-floating photosynthetic algae. And of course, as you can imagine, these often support a marine food web rather than trees or grasses. Okay, so on the terrestrial realm, we have grasses and trees that perform photosynthesis and serve as the basis of our food chain or food web. And here in the marine ecosystem, that is fueled by phytoplankton in the surface ocean. So in oceans, photosynthetic activity tends to be greatest near those coastlines, because as I mentioned on the last slide, the terrestrial realm feeds a lot of nutrients into the ocean. What nutrients am I talking about? I'm talking about these macronutrients that are needed for growth, like nitrogen and phosphorus. But also something else that you might not think about is iron. Iron is a key micronutrient for photosynthetic organisms because it uses this iron inside of those photosynthetic enzymes that make photosynthesis happen. Okay, so as this nitrogen, phosphorus, iron, and other nutrients wash offshore, in essence, they act like fertilizer to the open ocean, fueling primary production. So in the marine realm, we have a few different categories or zones. Ocean systems can be described by depth and proximity to shore. So benthic communities occur on the bottom of that water body, whereas pelagic communities and the pelagic zone are, by definition, the water column. So as a marine organism, you can either be benthic or you can be pelagic. And as you can see here, there are a couple different zones within the shelf environment and also the open ocean here. So we'll get into the zones now. The epipelagic zone has those photosynthetic organisms. As you can imagine, sitting here at the surface ocean, you are exposed to the most sunlight, and therefore you can allow photosynthesis to happen. So in the epipelagic zone, you have your primary production happening. You can remember epipelagic because epi means on top. Okay. Below the epipelagic zone, you have the mesopelagic zone and the bathypelagic zone. Bathy means deep, meso means middle, and of course epi means top. So really, you don't have to do much in the way of memorization for the zones of the pelagic realm because by their name, they tell you what they are. So the epipelagic zone and the mesopelagic zone, you usually find down to a depth of 1,000 meters in the open ocean. Below that, you have the bathypelagic zone, which reaches 4,000 meters. The deepest layers are the abyssal zone here and the hadal zone, which is deeper than 6,000 meters. Okay, so once you start getting into the abyssal zone and the hadal zone, you start getting very weird adaptations in your organisms. In order to live down here and make a living, you have to overcome extremely cold temperatures. It's extremely dark because, as you can imagine, that sunlight cannot penetrate much deeper than the mesopelagic zone. And also, you're experiencing very high pressures. Moving away from the open ocean and the deep ocean that is out here past the continental shelf, you can also move towards the shoreline. Shorelines are known as littoral zones, and the area exposed by the tides is known as the intertidal zone here. So in an intertidal zone, you experience tidal fluctuations where you can either have a low tide or a high tide. And an estuary is where fresh water meets salt water. And we'll talk about that in the next slides. So this is probably my favorite picture of the Earth. As you'll notice, it is nearly entirely ocean. And that is to communicate the point to you that oceans cover over 70% of Earth's surface. Most of the time when we pull up a globe, it's very North American centric. You've got North America in the middle and oceans on the left or the right. But if you just spin that globe a little bit, you'll be really impressed with the vast amount of ocean that covers the surface. So getting into different marine biological zones, the first thing to consider is that although the marine biosphere is really rich with life in general, most of that life is actually concentrated to shallow areas. Here we have an image of the White Oak River estuary where I've done some research. It is off the coast of North Carolina. And this is an estuary. Again, this is where salt and fresh water meet. And so the interaction of fresh and salt water creates unique ecosystems that are very vital to life. So you'll find estuary environments really teeming with lots and lots of different life. Another type of marine environment that's also teeming with life are our coral reefs. This is an image from Professor Unger, one of his diving expeditions. And you can clearly see that there's lots of different biological life forms here. So these ecosystems are highly productive. They actually thrive in nutrient poor waters. There's a lot of mutualistic partnerships and symbioses that occur in the coral reef environment. And so because of that, they are among the most vulnerable and endangered ecosystems on Earth because there are a lot of intricate ecological interactions, species-species interactions that fuel the entire productivity of the coral reef ecosystem. They're very vulnerable because corals are subject to what's called coral bleaching, and we'll talk about that in later lectures. But as you can imagine, if you take out one part of this functioning ecosystem, it can no longer function in the way that is healthy. Another ecosystem is the salt marsh. Salt marshes have emergent vegetation that dominates. These experience high salinity variations due to tides, but despite that, they are still highly productive ecosystems. These salt marshes usually border estuaries, and they get input from rivers to increase their productivity. So those are just a few types. Here's a couple more that I'm going to expose you to. So just a little bit more detail about these. Here we have an intertidal zone. Again, that's where you experience both high and low tide conditions. This is an image from the Bonaire trip that Dr. Unger takes his students on as part of the course to Bonaire. And it is offered this semester. In case you're interested in future semesters, you can always talk to Dr. Unger about this. But here we have a group of Maryville College students that are investigating and searching for intertidal zone critters. Next, we have shorelines. This is just an image of shorelines. And as you can see, a lot of garbage and debris washes up on these shorelines. So very vulnerable environment as well. We also have shallow ocean zones. As you can imagine, there's a lot of sunlight for primary productivity to happen, and many, many benthic organisms that occur on the sandy seabed. We also have the deep sea, which occurs in the hadal and abyssal zones. This is a creature with a bioluminescent lure, which means it emits light on its own. And the way that this creature works is it'll dangle this probe. It's kind of like a fishing line. It'll dangle it in front of its mouth and wait for an unsuspecting fish to think that it's prey for them. Unbeknownst to that prey item, though, what's holding that lure is something that's going to eat it right up. And so this is one of the many pretty weird creatures that inhabit the deep sea. I do want you to access this webpage, neil.fun/deep sea, to scroll through the deep sea. It'll really take you on a deep dive, forgive the pun, on the different creatures that inhabit the deep sea. In addition to that, there's also an extra credit opportunity. So when talking about freshwater zones, moving away from the marine environment and into the freshwater zones, there are a few characteristics that stream ecologists measure, including velocity, depth, temperature, water clarity, and the chemistry of that water. So talking in detail about streams and rivers, let's talk about their physical characteristics. Streams and rivers, of course, have variable velocity, even within a single river or a stream. And biological communities within streams and rivers are determined by channel size and location within that channel. So now I'm going to expose you to a concept that you might be familiar with or may have never heard about before, and that is stream order. Okay, so if you've ever heard the term first order stream, second order stream, this is where that comes in. So headwaters are typically found at higher elevations where you might have glacial melt. This is the first order stream. This is the source of the entire stream or river. And because it's a source, we call it the head or the first order. When you join two first order streams together, you get a second order stream. So over here, you have two first order streams. When they come together, their confluence is then a second order stream. This goes on and on. You'll have two second order streams that join together to form a third order stream, so on and so forth, until finally, for example, you reach the sixth order, like the case of the Mississippi River. So the convergence of two first order streams is second order. The convergence of two second orders makes the third order, so on and so forth. So because I can only do so much in illustrating this point with a cartoon, I'm going to allow this video to do the heavy lifting.
Hello, I'm Cody Whipple with the Pennsylvania Fish and Boat Commission. Today, I'm going to introduce you to stream order. I'm currently in a first order stream right now. Oftentimes, first order streams flow through heavily wooded areas. You can see I have a lot of rhododendron around me right now, which helps to cast shade on the stream year round, helping keep that water cold and clean. When you think about stream order, the number correlates directly to the size of that stream. So a first order stream is smaller than a second order stream. The lower the number, the smaller the stream. In order to form that second order stream, two first order streams, which I have represented with the black marker, have to come together, or a confluence. A confluence is where just one stream flows into another and two streams meet. So right here, we have two first order streams meeting to form that second order stream, which we have represented in red. The same goes for a third order stream. I have a third order stream represented with blue right here. Two second order streams have to come together to form that third order stream. And we continue on down the line. To form a fourth order stream, which I have represented in green, two third order streams have to come together to form that stream. to form that stream. You know, it is possible to have a first order stream flow into a third order stream, or even a fourth order, or even a fifth order, or even a sixth order stream. It's possible to have a second order stream flow into a fourth. The most important thing to remember is that that fourth order stream is formed by two third order streams coming together somewhere down the line. The same here, where I have a first order flowing into a third order, the third order still being formed by two second orders coming together somewhere. To learn more about Pennsylvania's water resources, you can visit fishandboat.com.
All right. So I thought that was a great explanation, and he was actually in the field at a first order stream, so I wanted you to be exposed to that. So there are a couple more terms that we need to expose you to. The idea of lentic and lotic water systems. So lentic systems are characterized as non-flowing systems. These are your lakes and your ponds. The other side of that coin are your lotic systems. These are characterized by continuous flow of water. In other words, your streams and your rivers. So lentic and lotic water systems are defined by the flow of their water. So taking a look at the characteristics of flow, you can have in a lotic system different components. First, we have riffles. These are fast flowing parts of that water body. Here we have in green riffles that are characterized as fast, shallow flow over boulders and cobbles that break up the water as it's flowing. So here in the big image, we have a bird's eye view of a stream. And here we have a profile view, a cross-section view, or just the side view. Okay, so here are the here are the riffles that are characterized by having lots of boulders, lots of cobbles, big old rocks to break up that flow. And so this is where the water is moving the fastest. In yellow or orange, we have what are called runs. This is where the flow is unbroken, it's smooth, and it is connecting those riffles to pools. Okay, so the run is coming forth from the riffle here, continuous unbroken flow until that water reaches a pool. And as the name suggests, the pool is slower flowing. This is where we have slow flowing deep water, often on the outside of bends in that stream or river. So that is the gross anatomy of the lotic system with your riffle, runs, and pools. We also can take a look at this in another way, in another dimension, and that is the depth dimension. So here is just a cartoon schematic of a lotic zone. This could be a river or it could be a stream. We have the riparian zone that border the water body. This is where we have riparian vegetation, providing organic detritus and materials and nutrients and shade for the organisms that inhabit this stream. So first on top, we have the main channel. This is where the water is continuously flowing. This is where you have fish living. They are swimming, they are living their life, they're finding their mates, they're finding their food, all in the main channel. Below that, you have the benthic zone. As we mentioned before, the benthic zone is found on the bottom. So this is the bottom of the stream. This is where you will find insect larvae. You'll also find crustaceans because they have to walk around on that benthic substrate. And then finally, beneath that, we have the hyperetic zone. This is adjacent to, but beneath the stream. So this is in some ways the stream bed beneath the surface. This is where you'll find rotifers, copepods, other invertebrates, including insects. They all live in the substratum in the hyperetic zone. So what do these organisms look like? Okay, they look a little bit like this. So back to those benthic organisms, we have fly larvae, including caddis fly larvae, which make these really intricate cases So if you ever get an opportunity to take Dr. Unger's invertebrate zoology class, it's really fun from what I can tell. And you can do some diagnostic testing on the different types of flies based upon the cases that they make as larvae. In addition, you'll also find crustaceans like crayfish scooting along the bottom of the benthic zone in your rivers and your streams. In your hyperetic zone underneath the benthic zone, you'll find rotifers that look like this, copepods that look like this, and other insects. Now, fun fact, rotifers get their name by their feeding mouth parts. So if you ever get to look at a rotifer under the microscope, it's this fascinating invertebrate creature. It has these mouth parts on the left and the right depicted here, and these spin around. They spin around, spin around, spin around, creating a vortex and essentially allowing them to vacuum food inside of their mouths. It is fascinating to watch under the microscope. If you ever get a chance to do it, I highly recommend it. But again, you'll find rotifers and copepods in the hyperetic zone. So of course, as with any environment or an ecosystem, animals that inhabit these places have to have specific adaptations that allow them to make a living there. So that includes body shape as well as feeding strategy. So in terms of body shape, these animals that live in the main channel, they have to be adapted to continuously flowing water. So usually these animals have highly streamlined torpedo-shaped bodies. Think of a fish. It looks like a bullet or a torpedo because it but it has evolved to reduce water resistance as it makes its way through the main channel. In terms of feeding, you have different habits depending upon if you're an organism living upstream or an organism living downstream. Upstream organisms tend to shred their material that they eat, including leaves, for example. So shredders will tear up leaves, and then anything that is unused in the upstream environment gets carried downstream to be eaten by collectors, which sift fine particles for their food. So all of that was the physical characteristics and the biological characteristics of the lotic system. Now let's transition into the lentic system. These are the lakes and ponds on Earth. They also include depressions or even standing water. So if it is a standing water body, it is a lentic system. These can be made naturally, like the Great Lakes, for example, which were scoured out by big glaciers during the last glaciation on Earth about 12,000 years ago. So that is a naturally occurring lentic system. Another naturally occurring lentic system is Mono Lake, which is found in California. This is a naturally occurring lake that is hypersaline. It's extremely, extremely salty. And that's because it's highly evaporative here. It's a very arid and dry. And so this is a closed basin lake where there's no inflow, no outflow. It's just a standing body of water. You can also have man-made lakes, including Tellico Lake. So shallow lentic systems with extensive surface area on the top usually have much more diversity than deep systems with low surface area. And I wrote usually here because in systems like Mono Lake, for example, where the environment is extremely salty, you have to be highly adapted to that space in order to live there. And so in that way, biodiversity is pretty low, but in general, in these lentic systems, they are pretty diverse. These again have different physical characteristics based upon depth. So talking about the different zones within the lentic environments, we have the surface and the benthic zones. So in the surface zone, we have the open water. This is the pelagic zone. It's also called the photic zone when we have photosynthesis occurring there. When we are near shore, we call that the littoral zone. The epilimnion is where water is warmed and mixed through a combination of heating up by sunlight and also turning over through wind. In the surface zone, we have what's called the thermocline. This is the area of sharp temperature change. And the thermocline represents the bottom of the epilimnion, where we have mixing of water. So the thermocline is where we have a sharp change in temperature. The hypolimnion is the water beneath the thermocline all the way through the bottom of the lake. Hypo means beneath or under. So you can remember that is beneath the thermocline to the bottom of the lake. We can also break these words down if they're too cumbersome or too jargony for you. So again, epi and epilimnion, epi means top. So this is the water on top of the lake. The word L-I-M-N, lim, is a prefix that means lake. So limnology, for example, is a study of lakes. So we can break down this word to top of lake. Makes sense. It's the top of the lake. Same thing with the word thermocline. Thermo means temperature. Cline is a change in conditions. So here we have a change in condition, specifically change in temperature, making the word thermocline. Again, breaking down hypolimnion, limnion having to do with a lake. Hypo means under. So of course, this is the water beneath the thermocline to the bottom of the lake. Okay, so all of that is a surface zone. Next, we have the benthic zone. This is the area beneath the surface to the bottom of the lake. This is where we have detritus from the littoral and pelagic zones that feed organisms below. As you can imagine, the benthic zone is going to be much colder than the surface zone. And in addition to changes in temperature, oxygen levels are also pretty low in the benthic zone. Now, what's fascinating is this phenomenon called seasonal flipping. So the conditions of the lake can change with seasons, and those changes in temperature that coincide with changes of seasons act to physically flip the water masses in the lake. So in this way, when we have flipping occur in a lentic system, this replenishes the oxygen and it circulates nutrients. And there is a YouTube video that I really want you all to watch about this phenomenon. It is called lake stratification. And this is a video specifically tailored to bass fisher people. And what they're telling you is how best to catch bass and do your fishing, keeping in mind some of these limnological terms like epilimnion, thermocline, hypolimnion, and oxygen concentrations and lake flipping. It's a really well done video. I really want you to watch it. So here's just a cartoon explaining what those different zones look like in a lake. And so here we have light and oxygen levels on this axis, with the most light and oxygen at the top, the least light and oxygen at the bottom in the benthic zone. The oxygen changes because in the top surface waters, you have photosynthesis happening. And those photosynthesizers are kicking out oxygen left and right. And so that's why you have a high concentration of oxygen in the top. Beneath the epilimnion, you have the thermocline, again, that rapid change in temperature. And then beneath that, you have the hypolimnion and then the benthos. Now, moving away from lakes and ponds, we're going to talk a little bit about wetlands and why they're so important, especially in a conservation framework. So wetlands are shallow ecosystems in which the land surface is saturated or submerged completely at least part of the year. Wetlands have vegetation that's adapted specifically to grow under these saturated conditions. These legal definitions are important important because although wetlands make up only a small part of most countries, they are disproportionately important in conservation debates and are the focus of continual legal disputes in North America and elsewhere around the world. So these are extremely important environments. Beyond the basic descriptions, defining wetlands is a matter of hot debate, believe it or not. For example, how often must a wetland be saturated? And how long must that saturated persist throughout the year? How large must it be in order to deserve legal protection? Answers can vary depending upon political and ecological concerns. So, although wetlands occupy less than 5% of the land in the United States, it's interesting to note that the Fish and Wildlife Service estimates that 1/3 of all endangered species spend at least part of their time in wetlands. So, wetlands retain stormwater and reduce flooding by slowing the rate at which rainfall um, reaches the river systems. So not only do they provide ecological services for the animals that depend on them to live and reproduce and carry out their life, they also provide ecological services to humans by slowing floods down. And floodwater storage is worth about 3 to 4 billion per year in the US. And so, therefore, by preserving these wetland ecosystems, we really do ourselves an economic service by using them and their natural capabilities. So we have different types of wetlands and we describe them by their vegetation. So swamps are wetlands with trees. They're also called forested wetlands and they look a little bit like this. In addition, you can also have marshes. These are wetlands without trees. They instead have these emergent vegetations like lily pads and short grasses. And then finally, bogs are areas of water saturated ground, usually composed of layers and layers of undecayed vegetation material that we call peat. And peat is the very first stage of making coal. And so, way back when we had the Carboniferous period on Earth, a lot of the land masses on Earth were covered in bogs and accumulating this undecayed detritus material, accumulating peat, and through burial and eons of geological time, that peat eventually became coal for us to harvest for fossil fuels.